Good afternoon, everyone. Thank you for joining us here in DC. I hope you're all having an awesome time learning about AWS. So in this session, we're going to talk about some of the newest innovations in serverless and how you can use these innovations to help you build some of your next generation applications. So my name is George Mao, and I'm a specialist solutions architect at AWS. In my past life, I was a software developer building all sorts of web applications. I'm responsible for helping our customers build solutions using Lambda, API Gateway, and the other services in the serverless platform. So all my contact information is down below, so I'm happy to answer any questions. So please feel free to ping me after this session is done. So in the last many years, over the course of the early 2000s, our industry kind of went through this transformation. And we started building these really large monolith applications. And as a Java developer, I used to build these applications, and I'd build these really large EAR files and WAR files, right? Has anybody ever built these before? Yeah, these are like 50, 60, 100 megabytes in size, and you would deploy them to some really heavyweight application servers. IBM WebSphere, BAA, WebLogic, Tomcat, JBoss, all of those, right? So now, how do we scale those? There's really only one way to scale those. You just deploy more, cluster more, add more power, and that's how you scale. So developers didn't like that because it was hard to scale, hard to manage, and everything was super tough to make simpler, right? Now, over the last 20 years, we've started breaking apart the monolith and started moving towards a microserviced architecture. So at AWS, we all do microservices. This wasn't something that AWS invented. The industry as a whole has been building this kind of architecture. So now the reason we do this is because of agility, right? All of our businesses want to move faster. We don't want to get stuck on deploying 100 megabyte WAR files that take 5 minutes to upload, right? So now a monolith, as you know, is typically built in a single technology stack. So if we take the example of a Java J2EE application, right, early 2000s, these applications are typically built in layers. And every single layer is built with the same technology, all Java, right? Whether or not Java met the use case well, that's what you had to do. So does anybody remember a design pattern called MVC? So Model View Controller, right? So this is where you would deploy your front end using JSPs. You would maybe use a controller like Spring or struts to create your kind of controller layer. Then on the back end, you'd have some kind of ORM framework, Hibernate, JPA, whatever it is to persist data. All of it's built with the same technology. All of it talks probably to one database. So now the opposite is true for microservice-based architecture. You're building really small applications, and these applications are probably built in different languages. You're choosing the right language that meets the specific use case of each microservice. Now, the only difference is that your microservices need to talk to each other. They need to be able to communicate, and they need a specific communication platform. So the real question that we were trying to answer as developers and engineers is as a businesses just want to move faster. They don't care how you do it, right? Developers want to focus on innovation. We don't want to worry about managing servers, dealing with network cards, CPU power, whatever it is that you don't need to manage in the cloud, right? So developers want to focus on writing application code that makes your business faster, better, and more innovative. So AWS has been building this serverless platform over the last few years to kind of help address these goals. So now we built this platform, and we believe that serverless has 4 primary tenets. So number one is you should never have to manage any infrastructure. Developers should never have to worry about provisioning hardware, patching operating systems, connecting network interfaces, setting IP addresses, dealing with vulnerabilities. All of this stuff should be handled by AWS. Number 2, scaling becomes out of the box. And we mean that because when you were back in the server world, you would scale, your unit of scale was a server. You would add more servers, make it bigger, and then keep going. So now in the serverless world, your unit of scale is by per request. So every request that you receive in your serverless application is delivering specific business value. And that's super important because now your billing model changes. So number 3, you're going to pay and you're going to be billed by delivering value. Every request that you serve is going to be delivering some sort of specific business value. And this is really cool because you're no longer bound to paying for idle instances. And businesses really love that because it can easily correlate your own cost to what you're delivering to your customers, right? And finally, the fourth point is that by using the AWS serverless platform, you automatically inherit all of the best practices, all the security features, and all of the high availability that AWS has built into our own platform. So essentially, serverless is an evolution of the operational model that you're already using in the cloud today. So if we look at this here, this diagram, the compute layer is generally built using AWS Lambda or AWS Fargate. And when you need to store data, you can use Amazon S3 to store binary files, or you can use Amazon Serverless Aurora to store relational database type needs. Or if you're building NoSQL applications, you can use Amazon DynamoDB. And then on the bottom row, when you need to integrate your applications and message between all of them, we have lots of different services available to help you with that. Everything from building REST services with API Gateway to SQS, SNS, and then step functions to help you correlate, build really powerful workflows, and the Kinesis to deliver real-time streaming applications. So today, our applications look a lot like this. Right? We have a lot of different microservices, potentially built with different technologies, Java, Python, Node.js are some of the most popular ones. But they all need to communicate with each other at the end of the day. And microservices do this through what we call an API, so a common programming communication interface. Right? And an API needs to be common so that all of these services can talk to each other. And at the end of the day, your services probably persist information to some kind of persistent, durable data store. So the question that gets asked a lot lately is, we have all of these pieces and we used to have a single monolith. Isn't it now a lot harder to manage all of these pieces as a developer and as an engineer? So AWS has a concept of the shared responsibility model. Has anybody ever heard of this model? Cool, so about half of you. So the shared responsibility model, simply stated, is just an idea that AWS will handle some of the operational needs, and then you as a customer will handle the other parts. And that line can actually shift depending on the services you choose, right? So let's take a look at the first row here, just the compute layer. So when you're deploying applications back on-prem, you had to handle everything from hardware to OS to patching all the way up the software stack to your application. So you're managing everything. Now, as you moved into EC2, to the right a little bit, you let AWS handle the hardware and you just handle the software and the OS up to the top of your application stack, right? Now, as you keep moving over to the right, if you decide to use AWS Fargate as a container service, you let AWS handle all of the heavy details and all the lifting, and you simply give Fargate a Docker container. And we scale it, we deploy it, and we manage it on your behalf. All the way to the right, now if you just want to work on application code and focus on the things that make your company innovative, then you can write your application code in AWS Lambda. So we'll take a look at that. So AWS Lambda is a compute service that allows developers to focus on writing application code. And typically, your Lambda functions are short-lived, and they're meant to be event-driven. So app developers can use pretty much any one of your favorite programming languages to write within Lambda, right? So we support 7 different programming languages today. We also support custom runtimes, which allows you as a developer to customize your own runtime, put it on Lambda, and run it as you would natively. So how many of you have written a Lambda function before? Wow, that's a lot. That's awesome. So now Lambda functions, as you know, don't have any tight coupling with AWS. You have to fit it with a little bit of programming model and a little bit of best practice design, but there's no specific library that you have to use to make it tightly coupled to AWS. So what that means is, as an app developer, you can easily port code into Lambda and then also port code out if you decide that Lambda is no longer the best place for your compute. Okay, so has anybody used Alexa before? Who owns an Alexa device? Like everyone, right? So you may not know, but when you woke up in the morning and you ask Alexa, what is the weather forecast this morning? Or what does my commute look like? Behind the scenes, we have this concept of skills that are responding to your request. And these skills are mostly implemented in Lambda. There's a lot of different ways you can implement the skills, but Lambda is the native way, out of the box way to implement Alexa skills. So when you ask your Alexa device all these questions, we're running Lambda functions. And if you want to see how this works, you can easily go onto the Alexa developer portal and just write your own Lambda function and then talk to it at home. So it's a really easy process to do. Definitely recommend everybody get out there and try it. So the Lambda programming model is super simple. It's based off of the idea that Lambda is triggered off of events. And these events can be triggered programmatically using the SDK in any one of the languages that we support, or it can be triggered using a CLI. So using a CLI command, you can invoke a Lambda function. If you don't want to do that, you can have AWS Lambda automatically trigger a Lambda function based off of events that are emitted from your ecosystem. So functions can basically be written in any one of your favorite programming languages. So we support Node.js, Python, Java, C#, Go, and Ruby. And also many different flavors of each language and different versions of each language, right? So some examples of a out-of-the-box event that would trigger a Lambda function would be like a change in a data state. So this is when you have, when you have a DynamoDB table that you're writing records to, and you want to respond to records that are incoming. So if you're familiar with SQL triggers, this is kind of the same concept. In DynamoDB, you can activate a stream which will capture a time-ordered sequence of things that are happening in your table, and then trigger Lambda functions according to your changes in your table and automatically react and perform whatever manipulation you need on that. Another example is a request made to an endpoint. So for example, if you're building a microservice, a REST API, and somebody has invoked your REST API, and you want to perform some kind of compute on that. So you can have a Lambda function respond to the HTTP request, perform the compute, and then return that response back out to your client, and never have any idle instances waiting for that work to be done. Another example is a change in a resource state. So for those of you who are uploading lots of files to S3, anybody using S3 to store millions of objects, yeah? So instead of having application servers that are constantly polling for new files, you can have S3 automatically emit an event and then invoke a Lambda function. So a really good example is for those who are dealing with image manipulation. And typically, when you upload images, the first order for your first task is to grab that image and then create different thumbnails, different sizes and resolutions for all of our mobile devices and laptops and computer screens. Instead of having a bunch of instances that are polling for this work, just have Lambda functions execute, do the resize, shut down, and then go away. So developers really love this experience because your first task is simply to write application code, right? There's none of this OS stuff you have to deal with. You don't have to choose application servers. You don't have to worry about bugs that get released by certain manufacturers. Developers really like to be able to get into Lambda, write your application code, and then immediately see it work. So let's take a look a little bit deeper into how Lambda works. So you can bring your own code, right? And number two, all you have to do is select your resource model. And there's really no configuration on Lambda other than choosing how much memory a Lambda function can use. And that can range anywhere from 128 megabytes all the way up to 3 gigabytes. And you would choose this memory allocation based on your compute needs, right? And based on your memory allocation, we automatically allocate both CPU and network throughput proportional to your memory allocation. So if you were to choose 128 megs of memory and you boost that up to 256 megs of memory, you would automatically get double the CPU and network throughput. So when you're building your Lambda functions, definitely try to understand what your compute needs are and then tune your Lambda functions to match those needs. Because you can actually make your functions run faster and use more of these resources behind the scenes instead of running slower and using less resources, right? So Lambda functions are super flexible. We support both synchronous and asynchronous invocations. So when you're building your applications, think of your use case and decide which invocation model works best. Typically, asynchronous invokes will allow you to scale much, much bigger and faster. It's fully integrated with nearly every AWS service. So many services emit events to Lambda, and Lambda using the AWS SDK can communicate with every single AWS service out there. The Lambda security model is based off of IAM. So if you're already familiar with IAM, there's nothing new to learn. You simply write IAM policies, attach an IAM execution role to your Lambda function, and that Lambda function is guaranteed to only have permissions to do whatever it is your role is specifying. So best practice in there is never include wildcards in those roles. I know it's very tempting to do that in development because it's easy. A lot of us do that, but try to avoid wildcards in any of your IAM policies as a best practice. So Lambda functions can access any public resource by default. You can also optionally allow Lambda functions to talk to resources in your VPC. And that's a process called VPC enabling your function. We'll talk about that in a little bit. So here is the anatomy of a Lambda function. So all Lambda functions need to have an entry point. And this is an example written in Java, Java 8 specifically. So a handler method is essentially equivalent to a Java main function, right? For those who have written Java. It's where your execution will begin. And you can name this method anything. I've named it handle request, but you can name it whatever it is you want. You just have to tell AWS what your method name is. So in this case, every handler method will take two parameters. The first parameter is the information or the object about what and why your function is being invoked. And the second parameter is a context object, which is metadata that AWS will generate that will provide all the details about this invocation. So in this example, I've written a Lambda function that's going to process somebody checking out of a hotel. Right? When you check out of a hotel, it's a very discrete event that you'll have, right? So that event object, that first parameter, will include everything about the checkout, the person, the name, the credit card, all of that stuff. The second parameter, the context object, will give you all of the information about who called it, all of the information about how long your function can run for, and all the security details around that. So you can use these two objects in conjunction to basically perform all of your application logic. Down below, your Lambda functions have to return some kind of value. So in this case, I'm returning a string, but you could return a different kind of object. In Java, you would return a POJO or a plain old Java object. In Node.js, it's pretty much the same thing. And then in Python, it would be a return as well. So now, after you've built your Lambda function and you're ready to expose it as a service, Amazon API Gateway is a managed service that allows you to easily create REST APIs. And AWS will manage all of the REST APIs for you after you've configured it and deployed it into what we call a stage. So API Gateway allows you to create really seamless integration from your client that's calling your API all the way to the backend that you need to invoke. Right? So we support clients that are on the internet or clients that are in your VPC as well, and that's called a private endpoint. Right out of the box, API Gateway will give you caching, authorization, authentication, throttling. All you have to do is basically set that configuration up. Behind the scenes, you can invoke almost anything. HTTP, Lambda functions, you can proxy to any AWS service, and you can even talk to services within your VPC. So now, these are REST-based APIs, and REST is really good for most application services and needs. However, for those of you who are building real-time applications, anybody building like dashboards and chat applications or things that need to refresh on a really quick basis, so REST isn't really great for that because you would have to make a REST call every single time you need to have new data. Now, with WebSockets, with WebSocket APIs running on API Gateway, you can easily create these really rich real-time applications. So in this case, when you deploy a WebSocket API, API Gateway will manage that persistent connection from your clients to API Gateway. And then you'll be able to invoke any one of your backends, just like you did with your REST service. So instead of having a fleet of containers or a fleet of EC2 instances holding those WebSocket connections open, API Gateway can do that for you. And you can still apply all of your authentication needs on top of that as well. So I definitely encourage you to look at the second type of API that API Gateway supports. So one of the primary drivers in our serverless world is to help our customers and help developers reduce all of that undifferentiated code that you have to write. And that makes developers a lot more efficient and definitely more innovative, right? So starting with cloud native load balancing. And application load balancers today have the ability to invoke and balance traffic across a fleet of Fargate containers as well as EC2 containers. And recently, we've added the ability for you to balance across a Lambda function as well. So this is very simple to do. You basically create application rules, routing rules, programmatically that define how a request should be routed. And you can use anything in the request to do that, and that's called advanced request routing. So you can capture anything in the request, such as the payload, the IP address, the query string, the path parameter, and then create really complex and rich rules and decide which compute engine on the back end should serve that request. Because one day, you may translate and move across different compute services, depending on how your business has changed. And you want to make that transparent to your customers who are calling your application load balancers. So the key idea here is that you can mix and match the services that make your use case the most valuable and make the most sense. Right? This creates a lot of flexibility for you as an application developer and also to serve your customers better. So the next thing that we were looking at doing was simplifying the amount of code and configuration that developers have to do. So those of you who have written Spring applications, right? How many XML files do you have to configure? Like so many that you can't even keep track of them, right? So we wanted to avoid that. So one of our goals here was to simplify it, make everything super easy. So when Lambda first launched, you basically have to package all of your dependencies with a Lambda function. So if you're writing a Node.js Lambda function and you need to use an image manipulation library, or if you need to use a WebSocket library that's not built into the Node platform, you have to download that package, npm install that locally, and bundle that up with your deployment package and upload it. So think of a scenario when you have a large company and you have multiple different Lambda functions. All of them have to do that. Right? You have to bundle the same application code, put it up with your Lambda function, and then upload it to the AWS service. So we've launched a service or feature called Lambda Layers to help address that problem. So Lambda Layers allows you to upload all of your common code to a layer. And common code is typically stuff like you may have a team working on logging, standardizing security, standardizing all sorts of stuff. And then providing that common code to all of your other developers, right? So you can upload these dependencies in a layer, and then at configuration time, configure a layer to work with a Lambda function, right? Now, the key important piece of this is that a layer is simply configuration detail. So there's no application code that you have to change. You can have up to 5 layers per Lambda function, and once you have a layer attached to a Lambda function, at runtime, AWS will automatically grab that layer and then add it to your Lambda execution environment. So your application code just assumes that that layer and all the dependencies in it already are in there. You don't have to make any code changes. So it helps you scale as your teams grow, and it makes it a lot better to manage common code across multiple teams, right? So how many of you are using Lambda functions to talk to VPC resources? Probably about 20% of you, okay? So Lambda functions, by default, operate and live in an AWS-owned VPC. So that's an important concept to understand. By default, Lambda functions all have the ability to talk to any public resource. So this includes anything on the internet, any of the public AWS APIs and SDKs, anything in your own VPCs that are public. So if you need to talk to a private resource, like an RDS instance, right? You wouldn't put an RDS instance in a public subnet, it would be in a private subnet. So in order to talk to a private resource, what you have to do is go through a process called a VPC enabling your function. When you do that, AWS will drop an ENI, so an elastic network interface, into the subnet that you're trying to communicate with. And then all traffic will be routed across that elastic network interface into your private subnet. So when that happens, all of your traffic routes through your private subnet, and then if you need to talk to any public resource, you have to go through a NAT gateway, right, out of your public subnet. So this process generally, in some cases, can take a few seconds to happen when you have a cold start. So in the next few months, you're going to see some really drastic improvements to how this process is handled. Right now, these elastic network interfaces are deployed at runtime. In the next few months, you'll see this happen at configuration time, which means you'll no longer see the few second penalty that you're seeing currently. So this will enable you as an app developer to create really stable response times for those API calls, for those services that have small and minimal latency SLAs, right? So now we've been talking about REST a lot. So REST is a very common design and communication platform, but there's actually another one that you should be aware of. AWS AppSync is a managed service that can help you create GraphQL APIs. And GraphQL APIs are an alternative way to help you build really rich, real-time applications that are pulling data from multiple data sources. So behind the scenes, AppSync can talk to all of these different data sources, Amazon Elasticsearch, DynamoDB, any HTTP data source, AWS Lambda, and even RDS. So when you make a GraphQL query, AppSync will automatically invoke these backend resources, consolidate the results for you, and then return one single response. And the power of this is if you have a network application that's really chatty, when it makes a lot of REST calls, and that hurts your performance, right? So if you were to implement this using AppSync, you could potentially reduce the amount of network calls being made and then speed up your applications. AppSync also supports an offline programming model. So if you're building applications that need to work offline, so if you have these laptops and you have phones and all these devices that need to operate offline and you need to be able to accept updates and look at information, and then when you do go online and you want to be able to sync all of that data, AppSync has that built in right out of the box. And probably the most powerful part of AppSync or feature is it has WebSocket real-time subscriptions built right in. So if you're building these applications and you respond to updates and look at information without you ever doing another query, you can use AppSync to do that. So let's dive into this a little bit and see how this works. So GraphQL is essentially a declarative data fetching syntax, right? So let's take a comparison at how you would build two application APIs using REST and using GraphQL. So on the left here, if we were to build an application that's pretty basic, it's going to manage a list of contacts, so like a phone book, right? In REST, in order to answer all of these questions about what you would do with a phone book, you need to create a lot of different REST endpoints, right? So that's because REST is essentially static in the type of data you're asking for and what it returns. So in a phone book application, you're probably going to need to be able to get all contacts, maybe search by state, search contacts by country or company, or some kind of search parameter, right? So all of these different /contacts, /contact information, /get contacts by state are all possible REST endpoints that you could create. Now, instead of creating REST endpoints, you could also create, instead of creating all these resources, you could also use query parameters and path parameters to do the same thing. But the point is that you have to create these things in REST in order to be able to implement them and respond to the customers that are calling your API. So when you're building a dashboard that's going to be implementing your phone book, you may have to make all of these network calls to build a dashboard. So in GraphQL, you can do this making one call to one endpoint. So what's really powerful about this is that the client that's calling your GraphQL endpoint simply needs to change the data in the request to ask for the data that they want back. So let's take a look at how this works. This is a sample of a GraphQL query. So this GraphQL query is get contact, and I want to get the contact with a contact ID of 111. However, inside my query, I'm specifying exactly what I want. So I want the contact ID. I want all of the information about my contact, including the name, email, and location. So in this case, the name and email are actually stored in a DynamoDB table. And typically, names and emails don't change that often, so we want to store this kind of static data in a persistent data store. We also might want to encrypt it and do all kinds of other data backup on it. Location of my contact potentially could change all the time. So I want to be able to invoke a dynamic resource to pull the location for this contact. So in this case, we're actually executing two resolvers. So when GraphQL receives this query, it's going to execute a DynamoDB resolver, and it's also going to execute a Lambda resolver. After it's completed both resolver executions, it'll return the response back out to the client invoking this API. So now, instead of doing multiple REST calls, in a GraphQL call, I can make one call and all of my data will come from multiple data sources. So let's take a look at one more example. So in this example, I'm still doing a get contact call, and the get contact call, I'm still asking for the same contact, 111. However, this time I only care about the contact's name, right? I might be building a dashboard or a smaller piece of my application that just has a list of names, right? So as a client, I'm still going to hit the same API, same authentication mode. I simply just want to change the data I want back. So when I send this query in, the single resolver for executing data from DynamoDB will be called, right? So AppSync is smart enough to not invoke my second resolver, my Lambda resolver. So in this case, we speed up execution, we reduce the amount of data being returned on the network, and then AppSync will handle all of that behind the scenes. So as an application developer, you have to build your resolvers behind the scenes, but once you're up and running, your application, your clients calling your GraphQL APIs can function very smoothly. So here's a resolver that's going to execute and pull in DynamoDB resource. Now, very recently, we've added the ability to do multi-authentication on your GraphQL APIs as well. So that means you can add different types of authentication across different fields or different objects in your API. So if you have a user who's connecting and they can only see the name and email, but they're not supposed to see the location, you can add directives inside your GraphQL schema, and then automatically respond and only return the types of data that your applications, that your users should have access to. So let's take a look at a server full comparison versus servers. So if you're building your applications in a server full world, you typically have to start by setting up your network. Setting up your network infrastructure, all the hardware behind the scenes, configuring your VPCs potentially, right? Your next step is configuring your host, right? This host configuration, as we know, is virtualized today, but you still have to configure all of the details about how to back up your host, how to launch, how to scale, how to do all of these things. After you've made the host decision, you have to make another decision. How do we load balance your hosts? Right? We have an operating system on your host, but how do we load balance all of these things? Are we going to use a software load balancer? Are we going to use a hardware load balancer? What kind of security and firewalls to put around these load balancers? After that's done, we need a policy in place and probably system admins to figure out how to patch and keep our operating systems up to date. Linux, Windows, whatever your favorite operating system choice is, all of these OSs need to have regular updates. So after you've done your operating system configuration, you're finally at the layer where you can do and choose your application server, web server, and finally decide on what programming language to build your application in. Right? And this process takes a lot of time. And if you have to change anything in this stack, you basically have to restart, right? Depending on how far down you want to go in this stack. So if we're building applications in Lambda, all you have to do is start with code. So the first thing you do is open up that console, start writing application code. If you're using non-compiled languages, you can go right into the console, Python and Node, you can start building really simple Lambda functions right in the console. For those who are building compiled languages, you do have to go through a compilation process. Lambda will not compile for you. So for example, if you're building in Java, you want to build your Java packages just as you do today, and then use Maven to package, zip, and then upload your Lambda functions to AWS. So I'd encourage you to use a newer service called AWS Cloud9. So Cloud9 is essentially an IDE that's operating on an EC2 instance that you own that sits in your VPCs, and it exposes a browser-based IDE to the developer. So all you have to do is use a browser to interact with this IDE, which means that you can actually program and write your applications on an iPad, right? Because it's going to use all of the power of the EC2 instance that you chose behind the scenes. So the great thing about that is its security is using IAM, so you could have multiple IAM accounts and roles and teams accessing the same Cloud9 interface. And you have direct access into resources in your VPC. So other than that, this pretty much wraps up our serverless update for today. And definitely thank you for your time. All of my contact information is down here. And we'd love to hear about what you're doing with serverless. At the end of the day, please complete the session survey on your applications. We definitely will need your feedback and help improve our future deliverables here. Thank you.